This video is to emphasize the concept of null space and null vectors in the context of example problems that we've already done. So first I want to go back and look at example 833. In example 833 we had a linear system of 4 equations with 6 variables, and the example was phrased in terms of an inhomogeneous equation. So let me write that equation first. It was 0x1 plus 2x2 plus 4x4. I'm sorry, 2x2 plus 1x3, etc. was supposed to equal 2. There were other equations. If we write it in matrix form, the first equation was 0, 2, 1, 4, 3, 1, and then the auxiliary was 2 for the first equation, and we had a 1, minus 1, 1, 0, 0, 0, 0. The third equation was 1, 1, 2, 4, 1, 2, 3, and the last equation was 1, minus 3, 0, minus 4, minus 2, 1, 0. So those were our 4 equations in 6 unknowns. So, of course, if this the sector, we consider the matrix A, and this we consider B, and we're searching for X such that A X equals B in the language and notation of chapter 10. So before we talk about the inhomogeneous equation, let's think about the homogeneous equation, A X equals 0. So the matrix A is row equivalent. That means after we do the Gaussian elimination to get it into row-reduced echelon form, the reduced matrix reads 1, 0, 3 halves, 2, 0, 0, 0, 1, 1 half, 2, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 0, 1. So this matrix has 4 leading ones, 1, 2, 3, 4, and 2 free columns. So the rank is equal to 4, that is its full rank, because for a 4 by 6 matrix we could only expect to have at most 4 leading ones, and in fact we do have all 4 leading ones, so it is full rank. There are no leading ones that are missing, and we have to have at least 2 free columns, and it turns out that we do have those 2 free columns, but no more than 2. So we have 4 leading ones and 2 free columns, so this 4 by 6 matrix is full rank, which means that the null space of A is 2. That means that there are 2 linearly independent vectors that will satisfy the equation AX equals 0, and effectively 1 associated to each of the free columns here. So if we write in terms of the variables, so our last equation for the homogeneous equation tells us that x6 must be equal to 0. That's the fourth equation. The third equation tells us that x5 has to be equal to 0, so x6 and x5 are not allowed to participate in any of the null vectors. then for the next equation, it tells us that x, well, let me say it like this. So for the free column corresponding to x4, so far there's no other relationship on x4, so let's make up a dummy variable. We'll call it alpha1. And then same thing for x3. We have a free column, so we'll call that alpha2. So the alpha1 corresponds to that free column, and alpha2 corresponds to that free column. Okay, and then moving on, our expression for x2 will involve both alpha1 and alpha2. So we see that x2 has to equal negative 1/2 alpha2 minus 2 times alpha1. So again, the alpha2 corresponds to this entry, and the alpha1 corresponds to this entry. And then finally, we have an expression for x1, which is equal to minus 3/2 alpha2 minus 2 alpha1, and again, the 3/2 alpha2 corresponds to the alpha2 column. And the minus 2 alpha1 corresponds to the alpha1 column. Okay, so this is the most general expression for a vector which satisfies the homogeneous equation. And so the point is that the null vectors are the two linearly independent choices. One of them we set alpha1 equal to 0 and alpha2 equal to 1, and vice versa. So let's call the first null vector x homo 1. Let's say that's for the case where alpha 1 is equal to 1, alpha 2 is equal to 0. That's simply equal to, so for alpha 1 equal to 1, x1 is going to be equal to minus 2, x2 is going to be equal to minus 2, x3 is going to be equal to 0 because alpha 2 is equal to 0, x4 is going to be equal to 1, and then x5 and x6 are always 0 for the null vectors for this matrix. And then we can ask about the other null vector, x homo 2. In this case, we take alpha 1 equal to 0 and alpha 2 equal to 1, and so we have minus 3/2 minus 1/2 1 0 0 0. Okay, and you can verify that if we act on the vector x with the matrix A, both a x homo 1 is equal to 0 and a on x homo 2 is equal to 0, you can verify that they're independent of each other. If you put them into a matrix, you can see that there'll be two leading ones in reduced row echelon form. So these guys are linearly independent, and so they make a basis for the null space. So x1 homo, x2 homo is a basis for the null space of the matrix A. Okay, we knew that since it was a 4×6 matrix, we were going to have at least 2 free columns, so there would be at least 2 null vectors. And it turns out that in this case, we didn't get any extras. All 4 possible leading ones were there. Now let's contrast that with a later example, example 10.5.6.